All right, so we are live now. Thank you everyone for joining us. Thank you, Mance, for being here.
Oh, thank you for having me. I appreciate the interest.
So Mance is the CEO of Swirls, and also Swirls has created Hashgraph. Mance, why don't you tell us a little bit about yourself, what Hashgraph is, essentially in a nutshell?
Sure, certainly. Well, so my background is computer science. I have been doing this since '93. I originally started in machine learning, working for the Air Force Senior Scientist for Machine Intelligence. And that was reinforcement learning with convolutional networks. Today, it's called deep learning. It's all the same stuff. I then taught computer science at the Air Force Academy and was a course director for cybersecurity, and then managed a massive software program for the Missile Defense Agency, and decided I wanted to be an entrepreneur. And so I quit. I left the military, and Lehman and I, the inventor of Hashgraph, Lehman Baird, and I started our first company, and it was an identity and access management company. If you or some of your viewers remember the old Palm Pilots, back in the 2000 time frame, long time ago, the old Palm devices, we built a distributed identity application using those Palm devices, sold that to a Fortune 500, managed product security for them, started our second company, Lehman and I, again in the identity space, sold that 6 years later to private equity, and then I ended up going to work for an identity company as a head of labs and architecture for that company, Ping Identity. And then we decided to commercialize Hashgraph back about 5 years ago. Lehman, I guess I should say a little bit about Lehman to set the context. Lehman and I have been working together since '93. We were working on that same team for the Air Force Senior Scientist of Machine Intelligence, doing machine learning research. We both taught. He also taught at the academy, and he was a full professor there. He's a PhD from Carnegie Mellon in computer science, and he has the distinction of having set the record for the history of the school in getting it in the shortest amount of time, 2 years and 9 months for a PhD from CMU, which is just an
It's a good
incredible
record
feat.
to have.
It is. And so beginning in 2012, he decided he wanted to solve this problem of distributed consensus, but the requirements he had in mind were much more stringent, if you will, or stronger than what is required just for a cryptocurrency. And so he didn't really start with blockchain. I mean, he certainly knew about blockchain, but the approach was entirely different. He started an entirely different place. And over the course of 5 years, I watched this. Well, actually, it was from 2012 through summer of 2015. I sort of watched this process unfold, and I've watched this many times with Lehman, right? He's always inventing things. It just happens that he invented something incredibly cool and at precisely the right moment in time in terms of the Hashgraph. And so I was watching this with Lehman, and in the summer of 2015, he sort of had an aha moment that you can solve these problems by doing a little trick with gossip about gossip, and we can talk about that in a moment. But there was this aha moment, and then everything unfolded very rapidly from that point. So 2015 through the fall, he formalized everything. I was able to watch this process, and he formally proved the properties of the algorithm. And it's very cool because, like on many other of his inventions, we would get together late in the evening at a Starbucks in Texas, just north of Austin. It's in Cedar Park. And we would be talking, and Starbucks would always shut down, and they would bag up all their old food and throw it over the dumpster. And we'd be sitting there at the table outside Starbucks going through these algorithms. And that's how this all started. And I decided that I was going to get Ping to invest, Ping Identity, my employer at the time, and they agreed it was a good idea to do so. And in Q4 of 2015, they first money into the company, and that's how Swirl's got its start. So that's my background, Lehman's background, and how we got to where we are today with the company.
Mm-hmm.
Hashgraph. So
Yeah.
I'll try to be brief, but it's easiest to do this in the context of everything else in the market. And it's really not that big of a market when we talk about the categories of consensus algorithms. Of course, the market's split into two parts. The public platforms that have an associated cryptocurrency most of the time anyway, and the permissioned or private networks. And the private networks don't use the same technology as the public networks. And so let's just talk briefly about that.
Mm-hmm.
The private networks use a category of algorithms called what we call leader-based algorithms. And this is Paxos and Raft and PBFT and RBFT and all these variants. There are dozens of variants of leader-based algorithms. And they all work basically the same way. The nodes in the network elect a leader. Architecturally, this is how it works. They elect a leader. They all send their transactions to the leader. The leader has the job of putting them all in an order and then sending them in that order back out to each node, and each node commits them to the underlying database in the same order. This is how they stay in sync, so to speak.
Mm-hmm.
The problem is that there is a leader, and the leader is a bottleneck, number one. It's also the case that if there's a leader that's in the middle of everything, then you can do a denial of service attack, a DDoS attack, against the leader. And all that's required is that any single node is compromised in any way. And as long as one node is compromised, then that node can send the IP address of the leader out to the botnet and direct the attack. Now, what would happen in this situation is very quickly the member nodes would realize the leader is offline, and they would elect a new leader.
Mm-hmm.
And then what they would do is, so the new leader would pick up the leadership responsibilities, but the attacker has to know the IP address by design. And so the attacker just redirects the botnet, and you follow the leader with the botnet.
So it's never ending indefinitely, that with this leader-based system that a botnet could take it down literally indefinitely.
As long as the botnet is attacking, as long as the attack is maintained, by attacking one or just a few computers, you can bring down the entire network. And this is something that most people never talk about. We didn't make this up. This is in the academic literature, right? I mean, we could point you to the paper that describes all of these attacks against PBFT, and it's true for leader-based systems in general. But nobody talks about it. And a lot of the banking infrastructure today is being built on top of platforms that use leader-based systems, right? It's an interesting situation. And then the other problem with leader-based systems is that they're not fair. And when I say fair, what I mean specifically is that if there is the opportunity for a single party to influence the order of transactions that the community ultimately agrees is the order, prior to the community coming to agreement, if they can influence the order, that's a bad situation. I mean, there's a whole range of use cases you wouldn't build on top of such a system. A good example is a distributed stock market. If one party can influence the order of the bids flowing into the market, then, they have tremendous power and they can be bribed. And you wouldn't trust the market to be fair in that sense. And it's true for auctions and for games and, just a full range of use cases that really need this fairness property. Leader-based systems are fair. The leader, by design, determines the order of the transactions and can drop transactions, delay them significantly.
Mm-hmm. As is with something like mining as well.
Exactly, and that's true. So let's go there. So that's the permissioned network market. Predominantly are using these leader-based systems. The public network market, of course, they're using proof of work today. And then the most modern systems are trying to move away from proof of work. We'll talk about them. But proof of work, your audience, I'm sure, understands this, but it's really simple. You have all the transactions flowing in to all the miners. The miners collect the transactions, put them into a block, and then they compete with each other for the privilege of publishing a block of transactions to the network of miners, which then would go on top of the chain, right? And that's what proof of work is. It's proving that you solved this puzzle, right? That you won the competition. and you have the privilege of publishing your block. Well, it's DDoS resilient, right? Because you can't predict which miner is going to win the competition, and so you can't direct a DDoS attack against this because you don't know where to direct it. So it's better than leader-based systems in that regard. The problem, as you pointed out, is that it's not fair. The miners unilaterally, by design, decide which transactions go in the block or which don't, and or they can drop transactions, leave them out, and they determine the order of transactions within the block. Okay, it's really expensive and it's slow by design, and we all know the problems with the throughput. So that's why we have leader-based systems in the permission world, is because you can't do much with 2 or 3 transactions per second. Right?
That's right. Yeah.
Exactly. All right. So the market has evolved. That's 2 of the 3 ways of addressing these problems that have been proposed. The market has evolved to try and move away from the proof of work-based systems by creating essentially models of economies. And what I mean by this is, if we assume that the players, or the participants, the miners, if we want to use that term, are operating in their self-interest, then it should be possible to create incentive structures that will result in the miners coming to agreement on the order of transactions if they're trying to make the most money possible. And it's loosely based on the idea of an economy. And the problem with this, I mean, they're very cool, by the way. And Lehman went down this path for 2 years. He struggled to try and design an economy-based solution that was also provably secure. And he wasn't able to figure out how to do that. And when I say provably secure, what I mean by that is, how do you take a complex system of incentives and formally analyze them and write math proofs that say entire categories of attacks are not possible in this system? He couldn't do that, and it's a worthy goal, and hopefully somebody will be able to do that in the future, but it's not been done to date. Mm-hmm. And so anyway, we have these economy-based systems that are now emerging in response to the proof of work-based systems. The question is, how do you, if you want to prove something formally, well, how do you do that? It turns out there are these 30-year-old algorithms we call pure voting-based algorithms. They exist in the literature. They're not practical. Nobody uses them because of the bandwidth requirements. But the interesting thing is, from an academic perspective, they have fantastic security properties. They achieve something called asynchronous Byzantine fault tolerance. This is the gold standard in distributed systems security. And it's not been practical. When we talk about practical Byzantine fault tolerance, this is what they're hoping to achieve, is practical asynchronous Byzantine fault tolerance. Nobody's been able to figure out how to do that until now. And for that reason, all of these BFT proofs have made assumptions that aren't reasonable. And like DDoS attacks won't happen in the real world, or that the evil players won't collude with each other. But is there any reason to believe that they won't collude? No, they're evil. They will collude, right?
Yeah, I think I do want to, if you want to just break it down for people as well, like what asynchronous Byzantine actually means, like where it can be like partially Byzantine or partially asynchronous, and what does that mean, and what are the implications of this?
Yes, absolutely. So here's the deal. Asynchronous Byzantine fault tolerance means that the attacker can have total control of the internet, and they can delay each node from talking to every other node for an indefinite period of time. And as long as eventually some messages are able to get through, as long as they don't shut down the entire internet forever, as long as eventually some messages are able to get through, then the community will come to consensus on the order of transactions. They will have 100% certainty, not probabilistic certainty, but 100% certainty that they have achieved consensus. and they will have 100% certainty that that order will never change in the future. That's what we mean when we say asynchronous Byzantine fault tolerant. It's an incredibly powerful attacker. And when we talk about partially synchronous BFT, what that means is that there are timeouts in the system, right? If there is a leader and you don't hear from the leader within a certain number of seconds, then you time out and you start over and you elect a new leader. If there are timeouts in the system, then you can design DDoS attacks against the system, right? And so, you know, these are the unreasonable assumptions that are made when people say, well, we've proven that we're BFT, but it's partially synchronous BFT, which means assume there are no botnets in the world.
Yeah, essentially, like when you're saying that you're Byzantine, but not fully, it's saying that you are safe in an imaginary world.
That's exactly right. You have to achieve, I mean, the gold standard is you need to achieve asynchronous BFT by the traditional classical definition, meaning that it's not probabilistic. You reach 100% certainty on the order of transactions, and you know that's never going to change. And there are no timeouts, so you can't be DDoSed. And as a bonus, it would be nice if there's this notion of fairness, and you can prove that the actual order of transactions flowing into the network is maintained. And that's what Hashgraph provides. It's the first practical implementation of asynchronous BFT, and as the bonus, it's provably fair. And that's what it is. Now, if you like, I'm happy to try and describe how it works. It's actually pretty simple conceptually. It takes a little bit to get your head around it. But
I think this was the thing when I was seeing the visuals. You guys have some really nice videos online, and the visuals help so much. So like for anyone who's listening, even after this conversation, I'd highly suggest that they go check out the Hashgraph website, because you guys have some really fantastic videos. One's a 45-minute video or so that actually lays it out in a graph, and it makes it very easy to follow. But let's give it a shot here. I think you'll be able to do a pretty good job explaining as well.
Well, so this is very conceptual, and the notion is pretty simple. If we have a replicated database, and of course that's what we're talking about here. We're talking about each node, each member of the network having a local copy of a database. All transactions to that database, all changes to the database have to go to everybody by definition. Everybody has to get every transaction to the database so that the databases can stay in sync. So that's the minimum bandwidth requirement. There are a lot of graphs, approaches to distributed consensus that are based on the notion of DAGs, directed acyclic graphs, that are being proposed today. The question is, what do these graphs represent? In our case, what Lehman realized, is that if Alice sends Bob a transaction, if she adds a tiny amount of information on top of that, basically, if she says to Bob, what's the last transaction or event that I created, and what's the last event that that somebody sent to me? In other words, who did I speak to last, in some sense, on top of the transaction itself? And then she passes that to Bob, and Bob gets the transaction, and Bob knows who Alice spoke to previously. Everybody is gossiping the same information. They're gossiping these transactions and with whom they spoke most recently. So they all get that information. If you take that gossip information, the gossip about gossip, you can build this internal data structure that is the Hashgraph, that describes who spoke to whom and when across the entire network. And everybody has the same information and the same Hashgraph, provably so. You take that, and you take one of these pure voting-based algorithms that I described earlier that exists in the literature, and instead of using that algorithm to cast votes over the network, which doesn't scale, you simply use the Hashgraph as an input to this pure voting-based algorithm locally, and for a given vote, for a given moment in time, you calculate in your head using this algorithm what each member of the community would have voted if they were to have cast the vote over the network. And by doing so, you come up with the same answer. Everybody's using the same input, the hash graph, with the same voting-based algorithm. They all calculate who would have voted, what each member of the community would have voted if they were to have cast a vote over the network. Because we're all doing the same thing, we all come up with the same answer. You have consensus without ever having to cast a vote. And you have all these fantastic properties that are proven in the pure voting-based algorithms. In other words, you have asynchronous BFT by doing gossiping about gossip with virtual voting. That's it. That's the trick.
So essentially, it's the fastest, most secure way to send information, and you're not sending big chunks of information. You're really only sending little hashes to reference other hashes and things like this. So this can move at insanely quick speed.
That's it. You have the transactions that have to go to everybody. You can't do better than that by the laws of nature. And with that block, if you will, if it's multiple transactions, it's a block. If it's a single transaction, it's just a transaction. You add 2 hashes. That's it. You add 2 hashes and nothing more. And you calculate the votes in your head and you're done. That's the magic of the hash graph. That's exactly right.
And so is this something where people will be able to build dApps upon and actually expand on this platform?
Absolutely. And well, so what we did as a company was started by addressing the enterprise market. I mean, we were a couple of guys that didn't have a reputation in the crypto space, cryptocurrency space, brand new algorithm that nobody had heard of. We knew we had to build some market validation and prove out the technology. We began to do that with ping identity and some identity use cases. We then went and competed for the credit union business. So the credit union saw what was going on with R3. They decided they wanted to do the same, and they created something called CU Ledger, Credit Union Ledger. It's the same as R3, but for the credit unions, the 6,000 credit unions in North America. We competed for that against IBM and Hyperledger, and we won the business. And that was our first big win. That happened back in the spring, and we'll be rolling out to those credit unions in the new year. And then since then, we filled up the pipeline with other financial services customers. The platform is nearing version 1, and what this is, it's not a public platform. It's a permissioned platform. The way I think about it is it's a consensus server. And just like there are web servers today, every company in the world uses a web server to serve up web applications. We think every business in the world in the future will also have a consensus server that serves up distributed applications. And that's what this is. It's a consensus server. It's written entirely in Java. Part of that reflects the target market, the enterprise market. But of course, no one is restricted to just using Java. But what you can do today, just by downloading the SDK, and it's on the website, anybody can download it today, is you can build arbitrarily complex distributed applications using Java, using the full power and libraries of Java, and that's what it is. That's what we've built to date.
Right on. So you're saying that people necessarily can they or can they not, if they wanted to build dApps on top of this, say today or next year, this would be a possibility for them?
They could do it today. No, so I want to be clear. I don't want to mislead. It's not version 1.0. It's not version 1.0. It's a beta version, and there's still features that are being added. Version 1.0 will be completed for the credit unions and be deployed in the new year for the credit unions. But we're not a year away from version 1.0. We're a few months. We're months away. In the new year, we should be achieving 1.0. But what you have today is do games. In fact, the demos we have are games and stock market and cryptocurrency and I forget what else. Oh, a file storage system. So there's a file system that can be used by developers, and you can build on top of it today.
Right on. So we have a couple questions coming in from people online. One of them is,
Sure.
exactly how does Hashgraph prevent against 51% attacks?
Yeah, so it turns out this whole 51% attack thing is really misunderstood.
As a 1/3 attack, yeah.
Yeah, exactly. You knew where I was going to go with this. It's a 1/3 attack. So there is a theorem that says you cannot do better than 1/3 of the community being evil. If 1/3 if 1/3 plus 1 of the community is evil, you can stop the network from coming to consensus. And this 51% rule, it works like this. And by the way, let me just say, Hashgraph requires 2/3 of the community being honest. And if 1/3 or 1/3 plus 1 is not honest, then like I said, they can do bad things. And that's the theoretical best you can achieve. The 51% rule is this: if it's the case that you can take a full community with not Hashgraph, but other consensus algorithms, you take the full community and you're able to partition it into 2 parts, and then you're able to have 51% of one of those parts, then you can do bad things. But what that means is you can have far fewer than even 1/3 of the community that's evil, and as long as they can partition the community and have 51% of the partition, then they can do bad things, right? So it's a fallacy to say that. So for example, blockchain has got this 51% rule. That's only true if you're counting the entire population, and you can't count the entire population because you can partition the population into parts and then attack it.
Say like using something like a firewall, for example.
Exactly. Precisely. That's it.
Right on.
So it's 2/3. You got to have 2/3.
Okay, right on. So this leads me to a little more technical questions about Hashgraph, if you're up for them.
I'm happy to do the best I can, and what I can't, I'm happy to get answers from layman back to you.
Okay, all right. So because all the rounds are done in little timestamps, and essentially like all the rounds project they say, okay, here's what time I was created at, here's what time I was created at. Who's actually doing the computation to decide, like, because there's a median that's being formed between those 3 times. Where's that computation happening?
It's happening locally on every machine. And so this is what, when we talk about the voting-based algorithm, let me just sort of at a high level describe what that's all about, because it relates directly to your question. If it's the case, well, let's start with timestamps. We have a transaction that flows into the network, and somebody, a member of the network, is submitting that transaction, and they put a timestamp on it. We can't trust that timestamp because they might lie. And so what we want to do is have the community of members assign a timestamp when they receive the transaction. So how long does it take the transaction to reach a majority of the community? And so what we might say is that we're going to look at the time, the median of what the community believes the time was that it was received. Let me restate that. The transaction flows into the community. Every member of the community receives the transaction, and they put a timestamp on it. We take that list of timestamps from the community, and we find the median, and then that becomes the community timestamp for the transaction, the consensus timestamp for the transaction. If we all are calculating that, and we all use this, the same population, then we'll all come up with the same answer. The question is, who is in this population? And, Alice may see some number of members are active and not active at one moment in time, and Bob may see a different set of members that are active or not active at a moment in time. And if the population is different for Alice than it is for Bob that's active, then when they calculate the median, they'll get different answers. That's the problem that we have to solve. The voting is all about coming to an agreement on who are the active members at a moment in time. And so we vote as a community to decide who are all the active members at a moment in time. When we're in agreement on who that list is of active members, then we know that we're all going to come up with the same median timestamp. And that's it. Once we agree on who the active members are for a given transaction, we calculate the median timestamp. We all have the same calculation. We all come up with the same answer. Every event has a consensus timestamp. We simply order those events by consensus timestamps, and we have a total order on all transactions. Done. That's the consensus on transactions, and that's what the voting is all about. Who is active at a moment in time, so that we all come up with the same answer on the median timestamp, the median timestamp.
Right on. Awesome.
That's it.
Yeah, thank you very much. So for the rounds, obviously you guys talk about that there's different, I guess, nodes or events that are famous or not famous is how you guys word it. And that's how the rounds are decided, and the order of events, which is the level up on blockchain where it's all just jumbled together. Maybe can you expand a little bit on how the ordering happens and how famous events play into that?
All a famous event is so when you have an event, you need a supermajority of, so when this is very abstract, right? It is a little complicated, but I'll try to make it simple. You have events, you have your hash graph, and an event, if it's visible by other events later in time, by supermajority of other events later in time, then what we know is that those computers that see it, if a computer is creating a transaction and creating a new event, and when it is creating its hash graph, there's a connection between an earlier event and a new event, then we know that that computer is turned on. We know the computer is active. And so famous events or famous witnesses simply means these are the set of computers that can see that event at a moment in time, meaning that they are turned on. And so if they're turned on and active, then we can all agree that these famous members or famous events are part of the population that we should include when calculating the median. And so a famous witness is it's famous if the set of, if the computer is turned on and can see it. Mm-hmm. That's what it's all about.
And another huge benefit of Hashgraph, or maybe it runs in parallel with other technologies, is computers can be on, or nodes can be on, nodes can be off, and it really makes no difference. Say if a node that's supposed to be working is turned off, then the gossip about gossip just happens in between the nodes that are on, and whatever's on and off, it's almost irrelevant.
That's exactly it. So, I mean, the nice thing about gossip is it's the most efficient way of getting a message out to a population. And it doesn't depend on there being a single route. I mean, as long as there is at least one route, then you'll get the information to the population. It's very resilient to network outages and that sort of thing. And what we have at this point is a very highly tuned gossip protocol to get those transactions out to the full population as quickly as possible. That's it.
Mm-hmm. So what do you see on the near and a little more distant horizon for Hashgraph and Swirls as a whole?
Yeah, well, Swirls is focused on the enterprise market. And I know there's a lot of interest in a potential public platform and that sort of thing. We aren't making any announcements at this point in time, right? But it's reasonable to assume that there will eventually be something out there. What I do want to stress is this: we are building a rock solid platform that addresses the enterprise market, and at some future point in time, that'll be the starting point. It won't be a white paper, right?
Right.
Right. It won't be a white paper. And so that would be the starting point. And, you know, things will unfold in the coming weeks and months. And so I would just say, stay tuned and subscribe to the Telegram channel. I don't mean to be coy, but that's the answer.
For sure. Yeah, I totally understand. There's been a lot of talk about Hashgraph, and this is a little more, this would be a little more coy, saying Hashgraph is here to destroy blockchain, and not coming from you guys, but from a lot of article writers. What would you I think that's a little more clickbait than anything, but what would you say to that on whether it's a symbiosis or a competition with blockchain for Hashgraph?
You know, every platform has its focus. Every platform has in mind solving a particular set of problems. And so I think there's plenty of room in the market for different platforms to provide value. And I mean, when you're building an application, generally, the range of problems you're trying to solve directly influences the architecture.
For sure.
And so if you're just trying to build a cryptocurrency, that influences the architecture. If you're trying to build something that's focused on smart contracts, that influences the architecture. And so there's room for different platforms to focus on different use cases, and we're no different in that. And, you know, there will be some sort of interledger protocol that eventually emerges, and we certainly would want to participate in those activities, and you know, that would be our position.
Right. So essentially, in a nutshell, if someone's holding Bitcoin or Ethereum and they're a diehard blockchain enthusiast, they don't need to go running screaming right now just because Hashgraph is on the horizon.
Not because of Hashgraph. No, not because of Hashgraph. No.
Why would you say they would have to go running screaming?
Oh, no. So people are asking me all the time, should you? And no, I'm not suggesting they should. And I'm not suggesting anybody should go running and screaming. I just don't give out advice on whether to buy Bitcoin or Ethereum or any cryptocurrency. It's an orthogonal question, right? It's not related to Hashgraph. Yeah.
Of course. Totally understand. Well, all right. Thanks so much, Mance, for coming on. I really appreciate talking with you, and have a great rest of the day.
Thank you so much. I appreciate the interest. All right.
Okay.